Good morning. I am Harshita Khurania and today I will be talking about real life applications of discrete probability distributions. Why probability distributions? Many real life situations involve uncertainty. Probability distributions help us estimate the likelihood of different outcomes and support better decision making in fields such as business, healthcare, manufacturing, finance, and technology. Now, let us discuss about each probability distribution in detail. Bernoulli distribution. This distribution models one trial with only two outcomes, success or failure. The random variable represents whether the outcome is a success or a failure. For example, an online customer either purchases a product or does not purchase it. This distribution is suitable because every customer visit has only two possible outcomes, making it useful for analyzing conversion rates. The graph shows that as the probability of success P increases, success becomes more likely than failure. Binomial distribution. This distribution models the number of successes in a fixed number of independent trials. The random variable represents the total number of successful outcomes. For example, a company can estimate how many customers respond to 100 promotional emails. It is appropriate because the number of emails is fixed and each response is either a success or a failure. The graph shows that increasing the probability of success shifts the distribution towards higher number of successes. Geometric distribution. This distribution models the number of trials until the first success. The random variable represents the trial on which the first success occurs. For example, a salesperson may need several customer calls before making the first sale. It is useful because businesses can estimate how much effort is required before achieving the first successful outcome. The graph shows that a higher probability of success leads to the first success occurring earlier. Poisson distribution. This distribution models the number of events occurring in a fixed interval of time or space. The random variable represents the number of events during that interval. For example, a call center can estimate the number of customer calls received in 1 hour. It is suitable because customer calls occur randomly but at an average rate. The graph shows that as the average rate lambda increases, the distribution shifts towards higher number of events. Negative binomial distribution. This distribution models the number of trials required to achieve a fixed number of successes. The random variable represents the total trials needed to obtain those successes. For example, a company may estimate how many customer calls are needed to achieve 10 successful sales. It helps organization plan resources when a target number of successful outcomes must be achieved. The graph shows the probability of achieving the required number of successes after different number of trials. Hypergeometric distribution. This distribution models sampling without replacement. The random variable represents the number of successful items selected in a sample. For example, in quality inspection, inspectors randomly select products from a batch to check for defective items. This distribution is appropriate because each selected item is not replaced, so the probability changes after every selection. This table compares all six distributions. Although all are discrete probability distributions, each one models a different real life situation. Selecting the appropriate distribution depends on whether the problem involves one trial, multiple trials, repeated trials until success, random events over time, or sampling without replacement. To conclude, each distribution has a unique purpose and application. In this presentation, I explained their concepts, interpretations, example, and real-life applications. Understanding which distribution best fits a real-world situation helps us model uncertainty accurately and make better decisions across different fields. The concepts, examples, and graphs used in this presentation are based on the references listed on this slide. Thank you.